let's look at a block of wood. Let's say I have a block of wood. Okay, just make it easier to imagine. Maybe let's say it's on a smooth table. Okay, if I think about applying a force, say to pull it to one side in one direction with a force of 2 newtons, and my friend pull it in the other side with a force of 2 newtons. They're obviously balanced. The forces are balanced, and the body, this block of wood will not move. Okay. But what if I do this? Now, what if I pull lower down? All right, I pull close to the bottom of the wood, and my friend pulls close to the top of the wood. We are both still applying 2 newtons, and we're both still pulling in the same in the opposite direction. So we might imagine that the two opposite forces, equal forces, should cancel. But if you look at this picture, can you just about imagine that maybe, probably actually, the top part will start moving to the right and the bottom part will start moving to the left. So yes, the block of wood will still stay here. It's not going anywhere because there's no resultant force to the left or right. But it will rotate on the spot, right? This block of wood is going to rotate clockwise. So because of this, we cannot actually say that when you have these two equal and opposite forces, we cannot actually say that this block of wood is in equilibrium, because clearly it's going to rotate. So for this situation, all right, because the two forces are not directly opposite each other, or let's be more precise, the two forces are not along the same line, okay, it would actually cause a rotation. And in this situation, therefore, we say that the forces are not in equilibrium, right? In the sense that something is not balanced. In this situation, it will rotate. Okay. Now this example, where we have two equal and opposite forces, in parallel directions, okay, but opposite, but not along the same line. This pair of forces has a name. It's called a couple. All right. The main things about the couple is that it has equal forces. The forces are in opposite directions. And most importantly, they are not along the same line. Not along the same line. So here we are. And the next thing we like to do is to have some way to calculate the size of the couple. So what that means is that for example, if I have, instead of 2 newtons, if say I have 3 newtons, then obviously it's a stronger, there will be a stronger rotational effect. So we can say that that's a stronger couple, okay? And or if the two forces are further apart, these two parallel lines are these two lines, the two lines of action of the forces are further apart, we would also imagine that there's a bigger maybe kind of moment from each force, and therefore a bigger turning effect. So how do we actually measure couple? How do we calculate the strength or the size or magnitude of a couple? The method is quite simple. Now, the strength of a couple is called a torque. It's a rather strange word. So torque of a couple, or in this case this couple. Let me write down how to calculate this. The torque of this couple is given by the force, 2 newtons, times the distance between them, rather between the two lines of action of the two forces. So let's say this distance is 0.5 meters, 0.5 meter. So therefore the answer is 2 times 0.5, which is 1 Newton meter. Now remember that I've said earlier that when you calculate work done and take force times distance, you also get Newton meter, and then in that situation, for the work done or energy, you can write Newton meter as joules. Okay, but in this case, for the case of calculating torques like this or moments, which is force times distance, we don't use the unit, the symbol joule for Newton meter. We just write Newton meter explicitly. We reserve the symbol J for just energy and work. So 1 Newton meter is the torque of this couple.